Okay. Well, yes. So I'm very happy and very excited to be speaking today. Today I'll be talking about some work that I finished up in my undergraduate degree at the University of Illinois. Like Sanan mentioned, I'm now a first-year grad student at Northeastern. Um, but yes, the work I'll be talking about was called Weighing Black Holes with Deep Learning, in collaboration with Joshua Yayu Lin, Devanshi Pratap, my PIs Xin Lu, Matthias Carrasco-Kind, and Volodymyr Kindratenko. This work was summarized in two papers, the first of which was published at Neural Information Processing Systems Conference, and the second of which is still under review, which was submitted to an astronomical journal. So as far as questions go, I will try my best to keep an eye on the chat, but of course, feel free to interrupt me at any point during this talk if you have any questions, in case I don't see. So the outline for today will be some background on supermassive black holes, and how we have observational evidence for them as well as theoretical evidence. Then I will spend some time talking about different applications of machine learning and neural networks. And then towards the end, I'll talk about specifically what we did, our motivation for doing so, and our methodology. So to start with supermassive black holes, the story really starts towards the end of the life of a star. So depending on the mass of a star, there are different possible outcomes for what will happen to the star after it dies. So for an average star like our sun will eventually enter a red giant phase when it expands, and it will shed most of its mass in what's called a planetary nebula. And what will be left over is a small corpse, in a sense, called a white dwarf. This is sort of a typical stellar life cycle, not particularly interesting. You get more interesting outcomes when you have stars with, in general, masses greater than 3 stellar masses. These enter a red supergiant phase, and they shed most of their mass in a very energetic explosion called a supernova. And basically, depending on the initial conditions, what can be left over is either a neutron star or a black hole. Obviously, in the context of this talk, what we're interested in is the black hole outcome. And this is largely due to inefficient nucleosynthesis while the star is still actively burning fuel, in a sense. It'll get to a point where gravitational force overcomes any pressure sourced by nuclear fusion, and then we're left with a space-time singularity. So from a theoretical perspective, we know from general relativity that the Schwarzschild metric allows for space-time singularities. Going back even further from the perspective of Newtonian mechanics, for example, it was hypothesized that there was nothing stopping a massive object from being created that had escape velocity greater than the speed of light. So the idea of black holes really goes back to Newtonian mechanics. Observationally, evidence for black holes is actually quite recent. We can observe the effects black holes have on surrounding gas or objects, and I'll show you some pretty interesting pictures and animations to confirm that. There are 3 major demographics of black holes that we know about. Typical stellar mass black holes range from the range of 3 solar masses to 10 solar masses. These evolved in sort of the way I described in the previous slide. Intermediate mass black holes will range from anywhere from 100 to 100,000 solar masses. And this demographic of black holes is largely unaccounted for. And it's a very active area of research as far as why we cannot see these readily, maybe what sort of dynamic sources the evolution and emergence of intermediate mass black holes, and yeah, why they're missing. It's a very active area of research. And then for our work, supermassive black holes are most relevant, and these range anywhere from 1 million to tens of billions of solar masses, so almost incomprehensibly large and massive objects. The evolution from black holes to intermediate mass black holes to supermassive black holes is actually unclear. Whether there is a direct evolution from one to the other is not even for sure. Like I said, there could be different dynamics that sources the emergence of these 3 different types of black holes. It is still a very active area of research. For example, the first evidence of intermediate mass black holes was actually detected in 2019 via LIGO Virgo. These are gravitational wave detectors. And so it really took, several leaps in technology and research to detect these objects, as they weren't detected in the usual observational sense that you might imagine. And this was actually a very big deal in the community, as well as the first overall detection of gravitational waves with LIGO. And so here is a animation showing the supermassive black hole at the center of our own galaxy. This is Sagittarius A star. This was actually what was awarded the Nobel Prize in 2020 to Professor Andrea Ghez from UCLA. And you can see here that these stars are all orbiting a massive object that we cannot see, and certainly that object must be extremely massive given that some of these orbits are quite hyperbolic. And so this was spectacular that they were able to observe this, and it was certainly worthy of a Nobel Prize. So to talk about supermassive black holes more, they're exclusively found at the centers of galaxies, and we typically call the center region of these galaxies active galactic nuclei. Quasars are actively accreting supermassive black holes, meaning they're eating mass in a sense. And because they're eating mass, the dynamics of the center region of the AGN are so luminous that the central region outshines the combined luminosity of the rest of the galaxy. And so that is why quasars specifically are interesting for astrophysicists and observers, because we can actually see the dynamics of what's going on in a sense. So looking at the geometry a little bit about supermassive black holes, we have the singularity at the center. So this is the space-time singularity. This contains all the information from the original massive object. I'm just saying star here. And then the event horizon is sort of the boundary that defines the black hole. As we know, this is the point from which light can no longer escape the gravitational field. There's also the accretion disk. So this is hot matter, dust, and gas, typically in the X-ray. So it's very, very hot, very bright. And this is sort of orbiting the black hole. And we also have relativistic jets, just jets of matter being spewed out from the poles of the black hole. And most of this has largely been seen from the point of simulations. Magnetohydrodynamic simulations, MHD for short, are very popular in the subfield because it's very difficult to, of course, get the sort of revolution to observe this going on actually in the universe. So I'm sure many of you have seen this image. This is the really groundbreaking Event Horizon Telescope image of the black hole at the center of the Andromeda Galaxy. This is actually a revision to their original image. Here you can see some magnetic field lines around the accretion disk, in a sense, or the halo of the black hole. I think the important thing to realize here is the scale that I set. So the diameter of this object on our sky is about 40 micro arc seconds. And so if you know anything about astronomical observations on the sky or just scale, this would appear smaller than a single dot we could observe on the sky. So the fact that, hundreds and thousands of scientists were able to collaborate all over the world to achieve taking an image like this is very, very extraordinary. And it's a beautiful image. And of course, no astrophysics talk would be complete without more pretty pictures. This is a screenshot from Interstellar in 2014. This is the supermassive black hole that they had in the movie called Gargantua. A fun fact about this is that Kip Thorne and other astrophysicists were actually consulted about how to create the visualization for this black hole. And at the time, I believe it was one of the most accurate depictions of a supermassive black hole in science. And so the fact that it appeared in a movie that was enjoyed by the masses is actually really something really nice for us scientists to see other people enjoying what we do. So now to sort of switch gears and talk about machine learning and neural networks. So machine learning in general is a study of how computer algorithms can improve through experience and by the use of data. And in general, this process is called training, which I will go into great detail in some further slides. Deep learning is a part of a broader family of machine learning algorithms. You can consider it a subfield of machine learning. And it's based on primarily the use of artificial neural networks. Artificial neural networks are just a quite flexible framework in which to do this learning from. The definition of deep learning will probably vary based on who you ask. Some people take the stance that, okay, this is deep learning because I'm using artificial neural networks. Some people require that not only are you using neural networks, but you're also not doing any sort of pre-processing on your data. In the sense that learning should be considered deep if the network is able to learn on raw data and not have me sort of push it in the right direction. For the purpose of this talk, I will only be using the case in which we're using artificial neural networks. And in the last 10 years or so, deep learning has seen a major increase in popularity with the advent of large data sets and powerful computers. I'm sure if you guys update or stay up to date on whatever archive of your choice, you'll see that the terms machine learning and or deep learning pop up more every day, to the point where it's even very difficult to keep up with the literature. But the advent of large data sets, we live in a world of big data, and specifically GPUs and parallel computing, high performance computing, have made machine learning and deep learning a more viable candidate to be used in research in the last decade. And of course, this is Hal from the movie 2001, A Space Odyssey. So there are different types of machine learning. So supervised learning is the learning regime where you're given some data. Here I've denoted it as X-train and Y-train. X-train and Y-train in general can be any sort of n-dimensional vector, or in the language of PyTorch, usually X-train is a tensor, not to be confused from tensors that are used in general relativity. But the goal with supervised learning is to predict some output Y test given some unseen input data X test. And so this is learning in the most traditional sense. And in general, you need labeled data to do supervised learning. And so you need to know which X train corresponds to which Y train. And like I said, the dimensionality of this is, up to discretion. Unsupervised learning is a learning regime in which you're not necessarily looking for an output, but you're trying to find underlying structure of your data. And so this could be if you have data in which you're not necessarily sure about what underlying relationships exist. Maybe the relationships that do exist are highly nonlinear. So with unsupervised learning, you can transform your data usually such that it preserves the variance from the original data. And in general, what you're trying to do is dimensionality reduction. So with unsupervised learning, you don't need labeled data, but you do need lots to learn from in general. And then lastly, reinforcement learning. This is probably the most exciting subfield of machine learning, in my opinion. This is saying, given some data X train, can my machine or agent, to use the jargon of reinforcement learning, find an optimal Y train so that the machine is minimizing some penalty function which I've assigned, and or simultaneously maximizing some reward function which I've assigned. Most state-of-the-art applications of machine learning that you might hear about in the news, for example, recent developments in protein folding by DeepMind, really excellent AI lab out of the UK, use reinforcement learning agents. And from a psychological perspective, reinforcement learning is probably most similar to how, for example, psychologists consider humans to learn. And so some current applications, regression and clustering algorithms fall naturally out of supervised and unsupervised machine learning. Computer vision is a subfield, which like the name suggests, concerns itself with analyzing visual data. And so this is the subfield that gives rise to driverless cars, for example, Tesla's AI autonomous driving system, as well as medical diagnosis. At this point, machine learning can diagnose some cancers better than radiologists can. Natural language processing is another subfield. This subfield concerns itself with sort of human voice assistants or text predictions. So Siri or Google or your Amazon Alexa are all byproducts of natural language processing, as well as when you're texting on your phone, for example, and a suggested text comes up. And then lastly, to mention DeepMind again, beating the world's best players in their board or video game at choice is something that DeepMind regularly enjoys doing. It's quite a joke that if you want DeepMind to solve a problem for you, make it a competition and they'll solve it. And so here on the right is this diagram of their game AIs primarily. AlphaGo was their very famous algorithm that beat the world's best player from Korea at Go. And since then, they've generalized the algorithm even more to something called mu0. mu0 is not given anything besides sort of, you can think the state space of the game. It's not told the rules or anything or any sort of techniques, and it has been able to master Go, chess, shogi, and Atari. They also have an AI that has learned to play StarCraft 2 as well. And then lastly, OpenAI has this neural network called GPT-3. GPT-3 is the largest neural network known to man, and it can virtually do anything you want it to do. There are animations of people asking GPT-3 to code for them, and it codes for them. Really spectacular stuff here. And it's actually quite hard to get your hands on GPT-3. So I believe when it first came out, there was a wait list. So in astrophysics, there are, of course, many applications outside of our own. And this is largely due to just the growing amount of data we see in astrophysics. And so observationalists love collecting data from large surveys. Data is usually on the hundreds of gigabytes, terabyte scale. And so beyond our own application of weighing black holes, solar flare forecast, for example, there's star galaxy classification. My collaborator, Joshua, had this excellent paper on event horizon telescope image analysis, in which he inferred some parameters from black hole images only using the image. Some parameters from black hole images, simulated black hole images, such as spin and mass, as well as gravitational wave detection. And there's more by the day. Like I said, it's impossible to keep up with the literature on the archive. But this has largely been fueled by just how much data we have in astrophysics, as well as how accessible, powerful computers are now. And so the backbone of AI, like I mentioned, are neural networks. Here on the left is an example of a sort of toy model neural network. This is a feed-forward neural network. You can see here it has some four-dimensional input data X and outputs some Y, here denoted by f of X theta. And so the structure of neural networks in general, you have what are called pre-activations, so the inputs of a neuron, and the pre-activations are a sum of the incoming signals, where each signal is weighted by some weight matrix, denoted here by Wij, and biased by some bias vector. And so this recursion relation on top basically describes how data moves through a neural network aside from training. And it's not really important here to understand the recursion relation itself, but I think the important thing to notice is that these neurons, an individual neuron, can be parameterized by essentially three things: the input data, the bias vector, and the weight matrix. And fine-tuning these parameters through this process of training is what allows the neural networks to learn. And then so each neuron either fires or not according to the value of the pre-activation, and then produces an output. And then in this recursion relation as well, there's this scalar value function sigma, which is called the activation function. And so in the old days of machine learning, the activation function primarily used was something called a sigmoid activation, in which the activation was 1 for, let's say, x greater than 0, 0 for x less than 0, to show the parallels between a biological neuron. Either it fires or it doesn't. It was found that the sigmoid activation function was actually difficult to train on. So now the most common activation function is something called the rectified linear unit. And the way this function behaves is that it is 0 for x less than 0, for example, but the magnitude of the activation scales linearly with the value going into the function. So you can imagine it's a linear function for x greater than 0, 0 before. And this is much easier to train on, and it's the state of the art, the standard used by practitioners in deep learning. And so here's just another diagram to show you the parallels between biological neurons, for example, and artificial neurons. Biological neurons, and I'm not a neuroscientist or a biologist, but have inputs from these dendrites, and then the body of the cell sort of transmits the information, and then it's released in the form of neurotransmitters. Artificial neurons are more or less structured in the same way, but instead of some biological process dictating their behavior, here we have well-defined mathematical processes. So there are different types of neural networks. So the example that I showed before it was a so-called feed-forward neural network, or a multi-layer perceptron. So this is the simplest and first type of artificial network. Basically, information moves linearly in one direction, uniformly through the network. It is a sort of proof of concept neural network. Since then, of course, we have several different types of layers and different neural networks. A quite popular option is a convolutional neural network. These neural networks are shown to work really well on image data. And the way these work is that, say, let me pass a kernel or a filter over a data set to learn features. And that kernel is determined by this process of training. So for example, down here, you can see that I have this grid. So, excuse me. I have this grid where on the left quadrant of the grid, it is all filled with tens and zeros. If I pass this filter over it, this is called a vertical edge detection filter. If I do piecewise matrix multiplication, sorry, I'm just trying to locate my cursor if I can. Oh, okay, no cursor, that's fine. But if I do piecewise matrix multiplication on the components of the image, you can see, so for the big blue square, if I pass the filter over it, I get a 0 because there's no sort of irregularities within that matrix. Similarly for the pink square. But for example, for the green square here, you can see that the filter outputs a 30. And so you don't necessarily need to know what the magnitudes of these numbers mean or anything, but the reconstructed data on the right, you can see shows that there's a vertical edge existing in my previous data. And so if you consider that these pixels or these numbers are not necessarily data, but pixels of an image, you can see why convolutional neural networks are so successful and so widely used on images. And then lastly, we have something called recurrent neural networks. I won't talk about these in too much detail as they're actually not the state of the art anymore, but this type of neural networks in general works well on time series data because it stores memory from previous inputs and outputs. In general, as you train more, as you go to T, as you take the limit as time goes to infinity, it'll become more difficult to access memory from your earlier inputs and outputs. And so for that reason, recurrent neural networks in general are pretty difficult to train, as well as maybe might not have as much success as some newer architectures. For example, the transformer. The transformer you can look at as an improved RNN architecture in the sense that it still operates very well on time series data, but instead of uniformly valuing all the data prior to your desired output, it can assign importance or an attention to whatever temporal data you have gotten. There's this remarkable paper that really characterizes the advent of transformers called Attention is All You Need. I highly recommend giving it a look if you're interested. Autoencoders are an architecture that are really useful when you're operating in the unsupervised learning scheme. Basically, this architecture can learn features from your data. So it can take some high dimensional, D-dimensional data and scale it down to some lower D-dimensional encoding from unlabeled data. And then the proof of concept of autoencoders and the reason they're so successful is that it can, in addition, reconstruct the original data from the dimensionality reduced encoding. And so in general, I would say autoencoders are probably most practitioners' architecture of choice when doing unsupervised learning. We also have what are called residual neural networks, which are very similar to CNNs, to convolutional neural networks. These are a bit different because they're much deeper and they generalize much better than traditional CNNs. These implement what are called skip connections. So in the sense that you may not have a linear flow of data just from one neuron to the next, but you can skip from, let's say, layer L to layer L+2 using skip connections. And the reason that they implement skip connections is for something called the vanishing gradient problem, which I'll touch on. But in general, these architectures generalize very well. And then lastly, I think probably one of my favorite architectures to come about in the last few years are GANs, generative adversarial neural networks. These can generate new data with the same statistics of input data. So where we see these in practice, sadly in deepfakes, if you know anything about deepfakes, this is essentially images of fake people or videos or images of people doing things they never actually did with the intention to deceive the viewer. And these are largely sourced by GANs. On a more beautiful side, there's been lots of AI created art. There's an app now that's very popular within some academic circles where people have been telling the AI the topic of their dissertation, and the AI, the GAN specifically, releases some sort of art, and it's usually very pretty. And of course, there's more and more by the month, by the year. Practitioners and theorists are coming up with new architectures all the time. So when you're actually training a neural network, it is not as simple as training, let's say, a person to do something. So after you fix your architecture and your neuron specific parameters, so like your activation function, how wide your network is, how deep it is, the network now must be trained over your data. And so, like I mentioned before, all the neurons in your network can be essentially characterized by its weights and biases. That is where all the information is stored. And the way these weights and biases are updated are through this process called gradient descent. So basically, you tell your neural network that here is some loss function, which I'd like to minimize. In general, your loss function will be a function of your, your neural network's output and your desired output. And basically, your loss function will operate as a distance metric between the two. And the goal here is that you want to minimize that distance metric. So example here I shown was mean squared error loss function, a very common loss function used, very flexible loss function. But of course, there's many of those. Deciding which one to pick is usually a case-by-case decision. And through the process of training, the goal here is, can I find the absolute minima of my, in general, n-dimensional loss landscape, which I've shown here on the right. Through this process of gradient descent, I would like to find the absolute minima, which corresponds to learning, to the most learning. And so with gradient descent, I take gradients, I move in the direction of steepest descent, and then I update my weights and biases through this process called backpropagation, which I won't go into too much detail because of time. And then there's other, in general, parameters such as the optimizer. This basically carries out the process of gradient descent and backpropagation. And then there are some parameters called learning rate and batch size. Learning rate, for example, dictates the time step of your gradient descent. So for example, if you have a small learning rate, it's likely you will achieve some sort of global minima, but your training time will be longer. On the flip side, if you have a large learning rate, training will be more efficient, but it is very possible that you could skim over the minima that you're looking for. And in general, these parameters can be very sensitive to, or your learning can be very sensitive to these parameters, and picking these parameters is something called hyperparameter tuning. And so there are difficulties in machine learning, of course. Overfitting is probably the most concerning. This is when your network learns the training data too well and cannot generalize. So the way we combat this is to split your data into training, testing, and validation sets. So the idea is that you train over your data, and then you simultaneously test each model on this test set. Then you, as the practitioner, can pick the model that has the best test set performance. But if that was your final model you picked, that would certainly inject bias into your results. So the idea is that after you pick a model, have it blindly perform on a validation set. And then it is important that you either stick with that model, or if you're not satisfied with the results, you refine something along your ML pipeline. This is just best practices. And then there's this vanishing gradient problem. And this basically says, if gradients become vanishingly small during learning, during training, the network will stop learning. So you can imagine here, as you take gradients, basically the underlying machinery of gradient descent is basically chain rule. So you can imagine, as I take gradients, if each gradient is small, small times small times small becomes vanishingly small. And you can get to this point where your network just can't learn anything else than it already has. And solutions to this are largely architecture specific. So residual networks, like I mentioned, that implement skip connections, or something called dropout layers, have been used to combat the vanishing gradient problem. If you're encountering it, it's generally pretty evident, as your neural network's loss function will be very small, but you'll be able to see that it's not learning anything useful. And then lastly, there have been some exciting developments in theory. As I know, most of us are theorists. So here at Northeastern, for example, professors Jim Halverson and Fabian Rula have been doing some really exciting work trying to understand deep learning from the perspective of effective field theories, for example. There is actually a textbook that's not actually published, but it's available on the archive, published this summer by Dan Roberts and Sho Yaida from MIT and Stanford, in which they basically tackle the deep learning problem from the perspective of physicists using effective field theory. It's really the first initiative of its kind, I would say. And then over the last couple of months, kernel methods have become more popular. Kernel machines are a sort of older mathematical construct, in my understanding, but they've gained popularity primarily through Misha Belkin from UC San Diego in his paper saying that over-parameterized neural networks allow interpolation. Which sort of perspective is correct, we do not know yet, but it's very exciting to see theorists tackling the problem of deep learning, as the hope is that for practitioners and even theorists that use deep learning in their research, this would make their lives more easier. We can demystify the black box in a sense, and one day, hopefully, hyperparameter tuning can become obsolete because at the moment, picking the right hyperparameters is more or less empirical. So now to sort of switch gears and talk about the motivation and method of our work. So why weigh black holes? Well, why not, I would say. But there are several outstanding problems which supermassive black holes can help solve. For example, we find quasars at very high redshift, less than a gigayear after the Big Bang. And the question is, how do they form so quickly? It's not necessarily intuitive that the ingredients would be readily available at such high redshift to produce such massive black holes. What is the relationship between supermassive black holes and their host galaxy? We know that we find supermassive black holes exclusively at the centers of galaxies, but the relationship between the two is still very poorly understood. And so how do they evolve together? And how does the evolution of one aid the evolution of the other? Where are all the intermediate massive black holes? Why is this demographic largely missing from observation? How do they evolve in time? And then lastly, from a cosmological perspective, understanding supermassive black hole mass may provide a new avenue to study the expansion history of the universe and constrained properties of dark energy. So just a little bit of background. I won't go into excruciating detail because a whole talk on its own could be made about problems in cosmology regarding dark energy, but a dynamic universe arises naturally out of general relativity. I'm sure some of you may have heard the story about Einstein introducing the cosmological constant into his field equations because he was a proponent of a static universe. It was actually Friedman who showed several years later that the cosmological constant can account for this expansion that was first observed by Hubble in 1929. In 1998, through the observation of type 1a supernova, it was determined that the expansion was accelerating much more rapidly than people had expected. And so now the question is, what is fueling this expansion of the universe? Of course, we call that dark energy. In lambda CDM cosmology, pretty much the simplest model, the most accepted model at the moment, lambda being the cosmological constant and CDM standing for cold dark matter, dark energy takes the form of a cosmological constant. And here's a pie chart on the right showing basically the energy density split up of the universe, where everything we know and love only accounts for 4.6%, dark matter accounting for 24%, and then dark energy accounting for more than 2/3 of the energy distribution of the universe.
And so, 5 minutes.
Okay, thank you. So now the question is, can I parameterize, or you said 5 minutes, Sinan?
Yes.
Okay, I might skip this then. Here's a 1A supernova, C feeds, very pretty. And so now to go on to our method specifically, we take time series data from the Sloan Digital Sky Survey. This has photometry in 5 bands. Basically, the important thing here is that this is just time series data. And we have about 10,000 light curves. And so in my previous notation, this is my X train and X test. Our targets or labels, our Y train and Y tests, are these black hole masses, also accessed through the Sloan Digital Sky Survey. And we match the data through this Python package called AstroPy. This plot here on the right, the red points are all the black hole masses, but the black lines are sort of the data we're restricted to because that has readily available photometry. Here is our data in supermassive black hole mass and redshift space. You can see there's some correlation between the mass and the redshift, which actually benefited sort of our learning process. We did use a feature called K-corrected eye magnitude. which basically gives us some indication of what the dynamics of the black hole are doing in the rest frame. And then we also computed something called colors, which are essentially the difference between bands, which provide information about the quasar's energy distribution also in the rest frame. So the important thing here is that we're handpicking some features that tell us about the quasar's dynamics in the rest frame, in addition to our time series data. And so time series, if any of you have ever worked with time series data in your research, you surely know that time series is incredibly difficult, especially when you have large gaps in your time series. So the way we sort of combated this was that we transformed our data into these 224 by 224 pixel tensors in PyTorch language. Essentially, the nuances of this transformation are not that important for the context of this talk, but what is important is that all the original information from the time series is encoded in this image on the right in some way that we as practitioners, as people, cannot necessarily understand, but the computer definitely can. And so, like I said, time series is very difficult. We supplemented our encoded information, so this image on the right, with known features by astrophysicists that we know would help with the training. And then prior to training, we normalize all the data to unit variance, zero mean, and split into training, testing, and validation sets. Here on the right is a principal component analysis of the human engineered features, showing at least in the context of this plot, the effect they have on the first and second principal components. It is worth pointing out MI here, that is dominating the second principal component, is what I mentioned earlier, this K-corrected I-band magnitude, providing information about the rest frame. And so the pipeline we used is a combination of an unsupervised learning scheme and a supervised learning scheme. We train this residual neural network, basically a CNN, on our encoded images in an unsupervised learning scheme. And we learn a 10-dimensional representation of that 224 by 224 light curve image. After this, we combine the encoded representation with our known features. So basically combining it into another dimensional vector. And we use that in the supervised part of our learning scheme using an MLP. And here are the hyperparameters down below. It was a 128 neuron wide, 5-layer deep network. We use the smooth L1 loss function, which if you read about in the literature, basically damps the effects of outliers, in this case towards the high and low mass range. And our network had about 30,000 trainable parameters. Here's just a brief overview of the architecture of the CNN. So there are just several convolutional layers here. And then towards the end, this is where we altered the architecture to optimize it for our specific application in estimating the supermassive black hole mass and redshift in this case too. So this is an overview of basically all I just said. I know it's a lot, but we go from our time series data, encode it into this so-called light curve image, pass that into our CNN, which we're in training as an encoder. We match that representation, so a 10-dimensional vector, with our known features. And now we enter the supervised learning scheme. We match our data with our labels because now we're supervised, and then we train and get the results. So the results here are shown. So on the left, we predicted quasar redshift. And I should have noted earlier, redshift here is redshift due to the expansion of the universe. It is not redshift due to motion in its local frame, for example. The black line on the plot is the ground truth. So you can imagine if the learning was perfect, all of the red and blue dots would be perfectly along the black line. In the case of measuring redshift, you can see the algorithm performed very well. There are these deviations. You can see for Z ground truth less than 1 and a little over 2. These were actually expected going into this, as there are some color degeneracies between quasars at these values of redshift. On the right here are results for mass. You can see that there's significantly more scatter, but as a proof of concept in estimating, black hole mass using deep learning, we're very happy with these results. The important thing to note here is that our estimates are virial estimates, meaning they have an intrinsic uncertainty. And so the uncertainty of our results actually matches the underlying uncertainty of our ground truth. So we did not expect to perform better than that anyways. And you can see that's denoted here, sigma equals 0.37 dex. Dex is an astronomer's unit for uncertainty. It basically means 10 to the 0.37, because On the case for mass, this is a log scale. And then finally, just some conclusions. So AGNet is able to learn from the light time series. It doesn't need a full spectra, which is very expensive. We were able to achieve an uncertainty in our mass prediction comparable to the systemic uncertainty in our ground truth. So we didn't expect it to perform better than that anyways. And this suggests that with higher quality data, you could achieve higher fidelity black hole mass estimates using this architecture. And yes, thank you.